Good morning, my dear student. On the behalf of KTM College, Nasik and Department of Chemistry of this college, I am Dr. S.R. Labhade. Welcomes you to the lecture on polarographic analysis. Student, in previous lecture we discussed some applications of polarography, such as number one is a qualitative analysis. That is the identification of electroactive species by using half-wave potential. Second one is quantitative analysis. By using diffusion current ID and Ilko equation. We also determine dissolved oxygen from sample. Number 4, we also determine two or more metal ions simultaneously by polarography. Student, in today's lecture we discuss remaining applications. That is, the fifth application is determination of copper and zinc in brass sample. Now we know that brass, that is a alloy. An alloy is a homogeneous solution of two or more metals. Here polarography, that directly useful for determination of copper and zinc in a brass sample in a single analytical level. Therefore, initially brass sample consisting of 50 to 90% of copper, then 20 to 40% zinc, about 0 to 6% tin, then 0 to 2% lead, and 0 to 1% iron. This is a composition of a brass sample, and here polarographic method is the best method for simultaneous determination of copper and zinc in brass sample. We discussed how to determine this copper and zinc in brass sample by means of polarography. Therefore, initially the brass sample is dissolved into concentrated HNO3 nitric acid and concentrated HCl, so that all the components, that is all the metals present in brass sample are converted. Metals are converted to their nitrate and chloride salts. Then this solution is made basic. Made basic by adding a buffer solution, ammonium chloride and ammonium hydroxide, ammonia buffer. This also acts as a supporting electrolyte in polarographic analysis. Then, in this case, brass sample having component copper, zinc, tin, lead and iron are converted to corresponding nitrate and chloride ion. These nitrate and chloride ion on treatment with buffer solution. Here, on treatment with buffer solution, lead, then tin and iron are get precipitated into their hydroxide while copper and zinc are converted to their amine complex. Therefore, tin, lead and iron are converted into their hydroxide, means that are converted into insoluble form, while copper amine and zinc amine are insoluble form, and those are converted into their amine complex. Then solution is filtered. And total filtrate is taken into polarographic cell. After bubbling the nitrogen gas, solution is electrolyzed using 0.0 volt to minus 1.1 volt potential range, so that amine complex and zinc complex are get converted into zinc amalgam and copper amalgam and produces a polarographic wave. The polarigram thus obtained gives diffusion current ID for copper and zinc, and ID of zinc is directly proportional to concentration of zinc, and ID of copper directly proportional to concentration of copper. Now here we have to discuss how this polarogram is obtained. Polarogram in this analysis is consisting of 3 stages of diffusion current. Here polarogram, that is I in microampere versus EMF in millivolt. Polarogram consisting of 3 stages in this fashion. First is for reduction of copper 2 plus to Q plus. This will be takes place at minus 0.04 volt. Copper plus 1 to copper 0. This will be at minus 0.22 volt. Then here zinc 2 plus to zinc at minus 1.0 volt. Therefore, in this case, ID of this here, suppose this is the ID, this is again second ID of copper, and this is third ID of zinc. Therefore, this ID is directly proportional to concentration of zinc. This ID is directly proportional to concentration of copper, or you may use this diffusion current for determination of copper. In this way, diffusion current measured for quantitative determination of copper and zinc in brass sample, and in this way, the single analysis is sufficient to determine zinc and copper in brass sample. Therefore, this is the best method for determination of copper and zinc in brass alloy. Student, now we discuss this application, that is a analysis of organic compounds. Analysis or determination of organic compound. We know that polarography, that is useful for determination of those analytes which are either oxidized or reduced within potential range 0.4 volt to minus 1.8 volt versus saturated caloric electrode. Therefore, analyze those are either oxidized or reduced within this potential range at dropping mercury electrode can be determined by a polarographic method of analysis. Therefore, here method also extended to determine the concentration of organic compound. Organic compounds having functional group like number one is carboxylic acid functional group, second one is carbonyl, third one is peroxide, then epoxide, then nitroso, amine, azo, then carbon-carbon double bond compounds and some quinones can be easily reduced in aqueous medium within this potential range plus 0.4 volt to minus 1.8 volt versus saturated caloric electrode and are determined by polarography. Therefore, organic compounds having these functional groups are directly converted to their another compound which is in a reduced form, and here if reduction is possible within this range, such a substance can easily be determined by polarography, and diffusion current is measured for quantitative determination of analyte. Student, now we discuss the last applications of polarography, that is called as a polarographic titration. Polarographic titration. Polarographic titration are those titration in which the equivalence point is determined by measuring the limiting current or diffusion current of the analyte. Therefore, equivalence point in polarographic titration is determined by measuring a diffusion current, or you can say a limiting current. Generally, a limiting current is measured as a function of ml of titan added in polarographic analysis. Polarographic titration. Student, we know that in polarography, diffusion current or limiting current, diffusion current is directly proportional to concentration of electroactive species. That means the species which undergo reduction at dropping mercury electrode. Therefore, diffusion current or limiting current is directly proportional to concentration of electroactive species which undergo reduction at dropping mercury electrode. Therefore, here if a part of electroactive species are removed from the solution, diffusion current decreases, and this electroactive species we can remove by adding suitable reagent. Therefore, if a part of electroactive species are removed from the solution by adding suitable reagent, or you may say titrant, then diffusion current decreases. And if total species are reduced or total species are removed, then diffusion current becomes equal to residual current. Therefore, this is the basis of a polarographic titration. In polarographic titration, limiting current is measured as a function of ml of titrant added, and limiting current decreases or limiting current is changes with the concentration of concentration of electroactive species. And if electroactive species are removed, then diffusion current decreases, and it would be reaches to residual current when there is no electroactive species present in the sample solution. Therefore, here this titration is called as polarographic titration when dropping mercury electrode is used as a working electrode, and similar is that is called as ampherometric titration when a other stationary electrode is used. Stationary electrode other than DME is used. Here, if DME is used, then it is a polarographic titration. And if same titration is carried out by using other stationary electrode like platinum, gold, silver, or graphite, then it is called as ampherometric titration. Because in this titration current is measured, and therefore it is called as ampherometric titration. Therefore, in polarographic titration, limiting current is measured. In ampherometric titration, a reduction current or redox current, that is cathodic current, is measured, and therefore it is performed by using stationary electrode. Polarographic titration is performed by using a dropping mercury electrode as a working electrode. When diffusion current or limiting current, all of this solution is measured, and if we obtain a polyarogram, then that polyarogram is having appearance like this. In this case, current in microampere versus EMF is equal to minus 44 volt versus ml of sulfate ion added. Now we have first polarographic wave in this fashion. That means here this wave is for a solution containing 50 millimoles of sulfate ion, 50 ml 50 millimoles of sulfate ion, when that means here 0 ml sulfate is added. Then here diffusion current is decreases when a 10 ml sulfate is added. That means here only a 40 ml 50 millimole of solution is available. Here 50 millimole of PB. Here 50 millimole 50 ml use this much diffusion current. Here 40 ml 50 millimole is remains unreacted, therefore diffusion current decreases. Again, in third case, diffusion current decreases when we add 20 ml. Then again, diffusion current decreases when we add 30 ml. Again, diffusion current decreases when we add 40 ml. Again, diffusion current decreases when we add a 50. Again diffusion current decreases when we add 50 ml. That means diffusion current becomes equal to residual current, and at 60 ml we also have a diffusion current equal to residual current. Therefore, this is the polarographic wave for that solution which consisting of 50 ml 50 millimole of Pb. This is a polarographic wave which having unreacted 40 ml 50 millimole of lead. This is a polarographic wave having a 30 ml 50 millimole of Pb. This is a polarographic wave having 20 ml 20 ml 50 millimole of Pb. This is for 10 ml and this is for 0 ml. That means there is no reducible species. Therefore, there is no wave. That means diffusion current or limiting current becomes equal to the residual current. This is a line of residual current, and here this is a limiting current. Therefore, in polarographic titration, limiting current reaches to residual current when titration reaction is completed. Now, this is a polyarogram that obtained in a polarographic titration. Now, we discuss how this polyarogram is useful for obtaining a titration curve. Now, in this case, actually we are measuring the limiting current, that is in microampere versus ml of sulfate ion added. Then here, for this we have maximum diffusion current when we add 0 ml. Therefore, this is a current when 0 ml sulfate is added. This is a current when 10 ml, 20 ml, 30 ml, 40, 50 ml of sulfate added. Therefore, here this is decreases in this fashion, and it reaches equal to the residual current. That means 60 and 60 ml. Therefore, here the diffusion current or limiting current is decreases, and it will be reaches to this is for 10, 20, 30, 40, 50, and after 50 it is constant. Therefore, 20, 30, 40, 50 and 60. Therefore, here this will be decreases in this fashion, and after that it is becomes a constant. Therefore, here we have two straight lines intersecting at equivalence point, and this is a equivalence point in polarographic titration. Therefore, in polarographic titration, when limiting current reaches to a residual current, then that is a equivalence point. And here in this case, as the electroactive species or its concentration is decreases, diffusion current decreases. And this is the example. Here we can determine Pb2 plus with sulfate ion at minus 0.44 volt, where Pb is electroactive. Therefore, here this is a titration curve in which diffusion current decreases as ml of titrant added. Then here a analyte gives the diffusion current, while product form does not give diffusion current and titrate does not give the diffusion current. That means as analyte concentration decreases, diffusion current decreases means only analyte gives the diffusion current. That means sulfate acid does not give diffusion current because after equivalence point diffusion current is constant, and product does not give diffusion current because here it is linearly decreased due to decreasing concentration of lead. Therefore, here we can also perform this polarographic titration for different types of analyte that may be electroactive or that may not be electroactive. If analyte is not electroactive, then reagent is selected electroactive. Sometimes analyte as well as reagent both are electroactive, then also we can perform the polarographic titration. Suppose for example, we have different titration curve. In this case, suppose for example, we have first titration curve in this fashion. Here only analyte is electroactive. We have second titration curve in this fashion, in which suppose for example, nature of titration curve is like this, in which the reagent is electroactive. That means analyte and product does not electroactive because diffusion current does not changes, but after equivalence point it get increased. This is a titration curve where analyte and reagent both are electroactive. That is the potential at which analyte and reagent both are electroactive. Then we have V-shaped titration curve. Here only reagent is electroactive. Then we have a titration curve like this, L-shape. Here inverse L-shape is obtained when analyte is electroactive, reagent and product does not. Similarly, this is the nature of titration curve in which we have a nature like this. In this case, a analyte and product are electroactive. That means if product is analyte is converted into product, that is the diffusion current. Therefore, analyte and product both are electroactive, but reagent does not. And suppose for example, next type of titration is like this. In this case, here the product is electroactive while analyte as well as reagent does not. Therefore, we can perform this polarographic titration for different types of analyte. If analyte is electroactive, then we easily perform. If analyte is not electroactive, then we can use reagent electroactive. If reagent and analyte both are electroactive, then also we determine that by using a polarographic titration. If analyte and product are electroactive, then we have nature of graph like this. And if analyte is not electroactive, even reagent is not electroactive, then we also determine if product is electroactive, then we determine that analyte by polarographic titration. Student, this is all about the all of polarographic titration. Now it's time to invite you to my next lecture. Thanks for joining with me. Wish you all the best. Keep learning. Happy learning.